Okay, so now, so x Cp over C is equals to 1 over 4 minus Cm about quarter chord over Cl. So Cm and Cl are already given. We can directly apply them here. So minus 0.09 is the Cm about C over 4. And Cl is 0.85, so XCP over C is, or XCP is equals to 0.356 times the chord length. That means, in actual case, the CP, especially for the symmetric aerofoil, the CP is located at quarter chord. That quarter chord is 0.25 times C. But here it is about 0.356. That means the location of the action of resultant forces shifted to behind of behind of the quarter chord. Okay, so that is 0.356. That is the meaning. So in the case of NACA 4412, this NACA 4412 is not symmetric aerofoil. It is cambered aerofoil. For symmetric aerofoil, the NACA 4-digit representation starts with NACA 00, then the next 2 digits will come, like NACA 0012. Right? That is called symmetric aerofoil, as we have discussed in your flight theory course. Again, let's continue with another example. Consider the DC-3, that is Douglas DC-3 aircraft, which is actually Ethiopia also have this kind of aircraft at the very beginning of hiring of the aircraft. So for that, the chord length is 15.4 is given at a cruising velocity 188 mile per hour at sea level, and the moment per unit span at the aerofoil R mc over 4, which is equal to minus 0.71. Moment is given, cruise velocity is given, moment about leading edge also given, which is minus of 3.9 feet pound per feet. So that is, again, moment about leading edge, moment about quarter chord, and the chord lengths are given. Again, the flight velocity also given. So it is given in mile per hour. So you can convert it to feet per second. So in this case, the chord C 15.4 feet, velocity 188 mile per hour. Moment about quarter chord is minus 1071, and moment about leading edge minus 3213.9 are given. So what is required here is the lift and the XCP. So XCP is required, lift is required. So in order to find the lift, we can directly use C over 4 L is equals to MC over 4 minus M about leading edge. Directly applying this, we can immediately find the lift. So the lift becomes, just it is a matter of mathematics. So C is already given 15.4. Applying that, we can directly get lift. And again, using similar equations from the previous, XCP L prime minus of XCP L prime is equal to moment about leading edge. So from that, you can find XCP, which is equals to 5.774. That is just XCP. So the force and the moment system acting on the aerofoil is uniquely specified by giving the lift acting at any point on the aerofoil and the moment about that point. ስለዚህ ይህን ካል ስለተለያዩ ስለ ሲፒ ሴንተር ኦፍ ፕሬዠር የተወሰነ ነገር እንዳወቃችሁ ነው የማስበው። ለምሳሌ ፎር ሳይሜትሪክ ኤሮፎይል ምንድነው ሴንተር ኦፍ ፕሬዠር እና ኤሮዳይናሚክ ሴንተር የሚል ደግሞ ይመጣል። The aerodynamic center is the center in which the lift and the drag acts through. The aerodynamic forces, the lift force, the drag force, as well as the aerodynamic moment acts through is called aerodynamic center. So for the symmetric aerofoil, aerodynamic center and center of pressure acts at the same point. But in the case of cambered aerofoil, they will not. So ይህን ይመስላል። Now let's see the dimension analysis. እዚህ ጋር ብዙ ኮምፕሊኬትድ የሆነ ዳይሜንሽን አናሊሲስ ውስጥ አንገባም፣ ግን ኢምፖርታንት የሆነ ፖይንት ብቻ አይተን እናልፋለን። ኢንተረስትድ የሆነ ሰው መጽሐፉን ማንበብ ይችላል። So consider this is what we call the Buckingham-Pike theorem, and on that, consider an aerofoil at a given angle of attack, and the resultant aerodynamic forces are normal force here and axial forces in the axis directions for the aerofoil. And the lift is acting perpendicular to up, and the drag is parallel to the free stream velocity. So these forces are given. And all of them are of the part of resultant force. You see, this is a resultant force. You can resolve this resultant into lift and drag, or you can resolve this resultant force into the normal force and axial force. So our main aim is with lift and the drag, so that let's give emphasis for that. So this resultant force depends on 5 different situations. One of it is free stream velocity. So the direction of the free stream velocity is one of the factor. The free stream density, the density in which our aircraft is flying. Maybe it can be at some altitude or it can be at sea level. Again, the viscosity of the fluid. Our fluid is what we call, it is air. And the viscosity of the air is already known. Therefore, that the shear force is directly proportional to the velocity gradient. Therefore, the proportionality constant in this respect is what we call the viscosity coefficient, that the viscosity coefficient is given, so that it is mu times dv dy. And another factor is the size of the body. That means the chord, the length of the chord length dimension. And the third, and the last one is the compressibility of the fluid, which is the rate of change of density. Okay, so in our recent aerodynamic topic, we consider the incompressible flow. So incompressible flow is related with densities remain constant. Okay, so if density is constant, we might not care about the density condition here. So, however, we have to know the density of fluid is also in the case of compressibility. So that compressibility is related to the variation of density throughout the flow field. And the aerodynamic forces and the moments should be sensitive to any such kind of variation. And in turn, the compressibility is related to the speed of sound also, because that the speed of sound is equal to radical of rho gamma RT, and it is related with the compressibility. So from that, we can represent the variation of resultant force as a function of density, as a function of velocity, as a function of chord length, dimension, as a function of compressibility or the viscosity, and the function of airspeed, or airspeed is related to compressibility. So these are 1, 2, 3, 4, 5 variables. So the resultant aerodynamic force is a function of this all. Okay. And then the dimensionless force resultant coefficient is given with CR is equals to R over, R is the resultant force over Q times S. And that Q is half rho V square, as you know. Okay, so CR is a function of also another important aerodynamic variables, which are Reynolds number and the Mach number. So Reynolds number is the number which you are familiar with it in your fluid dynamics course. And the Mach number also is the one which we have discussed, that the ratio of flow speed divided by sonic speed. Therefore, the lift and the drag are also components of the resultant force, as in lift and drag are resultant component of resultant force, so that they are a function of Reynolds number and Mach number. Okay. Again, the moment also a function of Reynolds number and Mach number. So it is better what that Reynolds number, just for highlight, because you are familiar with it. So for the body given, for a given shape at a given angle of attack, the lift, drag, and the coefficient of moment are generally dependent on Reynolds number, Mach number, and angle of attack. Okay, for a given angle of attack, they are a function of these three quantities, in addition to the previous stated 5 variables. Okay, so these all are function of, they are affecting the total resultant load. So just to give you highlight, that Reynolds number is just a dimensionless quantity, and it is just inertial force divided by viscous force. And it is it is formalized simply rho VL over mu. So for round object, L is D in our case, diameter. Rho V, D. V is velocity, rho is density, L is the length, and mu is the viscosity, or what we call fluid viscosity. So we can actually represent it in terms of kinematic viscosity. V times L over the mu, or this is mu, actually what we call this one, you can check it. Anyway, that's kinematic viscosity also is 1 over density. Kinematic viscosity is equals to 1 over density. And the unit is of the reverse of densities for that. So if Reynolds number is less than 100, no, 1000, we consider the flow is streamline flow, or non-turbulence or flow. But if that Reynolds number is greater than 200, we consider it as turbulent flow. And in between 1000 and 2000, it is a kind of unsteady flow. So that is just your revision about Reynolds number. Yeah, so for laminar flow, the Reynolds number, the fluid flow is smooth and the viscosity force dominates. Therefore, for the flow in pipe, this works. For turbulent flow, which occurs at high Reynolds number, and it is characterized by the coitic, or with eddy kind of vortices are there. So inertial force dominates the flow here in the turbulence flow, and transitional flow, which occur in between the two, is laminar and the turbulence region. So similarity approach is one of an important approach here. So according to the law of similarity, the two flows are dynamically similar if they have the same Reynolds number, even if they are different in size. So some of the shapes or size may vary, but if the Reynolds number is the same, then we call the flow are similar flows. This principle allows for the use of scale model in the wind tunnel, because in the wind tunnel we put representative part rather the whole model. We are not going to place the whole aircraft in the wind tunnel. We put a small representative or the scaled 1/10 or 100ths of scale of that aircraft will be placed in the wind tunnel test section. For that, we consider the flow similarity condition. So that is useful for modeling the object in the wind tunnel and predict the behavior of that object with the full scale. Okay, so that is what we call prototype modeling principle. So this is just a Reynolds number. It is relationship between. So yeah, you can observe also the boundary layer condition, the length, and the relation between different. So this is just a further explanation on the Reynolds number. Again, flow, turbulence flow, laminar flow, and some transition. Okay, so let's discuss more about flow similarity. That is an important part of our discussion. So consider two different flows, flow fields over the two different bodies. By definition, different flows are dynamically similar if the stream pattern are geometrically similar. Again, the distribution of velocity ratio, pressure ratio, temperature ratio, and other flow field variables ratio throughout the field are same. And if the force also coefficients are the same, then we can call it as the flow similarity, or the flow is called similar. So if the non-dimensional pressure and shear stress distributions over different bodies are the same, then the non-dimensional force coefficients will be also same. So that's why the flow similarity analog will help us to model a small amount of prototype model with the large, huge aircrafts and other space vehicles. For any aerodynamic application, the Reynolds number and the Mach number are the most dominant similarity parameters. We give emphasis for the Mach number and Reynolds number. We call the flows over given geometrical similar bodies as the same Mach number and as the same Reynolds number are dynamically similar, and hence the lift drag moment coefficient will also be identical for the body. Okay, so that is what you call the similarity principle. So this is the main point in which we are validating the wind tunnel experiment testing with our real application. If the scale of model, or if a scale model of a flight vehicle is tested in wind tunnel, the measured lift, the measured drag, and the moment coefficients will be the same as for the free flight, as long as the Mach number and Reynolds number are the same of the wind tunnel test section flow. ስለዚህ በዚህ ኬዝ የዊንድ ታናል ቴስታችን የምናመሳስለው በዚህ ነው፣ የማመሳሰል ማለት ነው። For example, we can see here two different cylindrical objects or circular objects are there. So the geometrically similar bodies are there. One is D1, another is 4 times D1. That means 4 times greater than. Therefore, the velocity of the first geometry is V1, density ρ1, temperature T1, and the flow pattern is here. And this is 4 times greater than that. So V2 is equal to 2 times V1, ρ2 is equals to ρ1 over 4, T2 is equal to 4 times T1. So this is the relation that happen in between them. Because density is equal to mass over volume. So that is, the volume is inversely proportional to this thing. So we can make similarity here. So consider the flow over two-cylinder circular cylinder, one having 4 times the diameter of the other. So the flow over the smaller cylinder has a free stream density, velocity, and temperature given by ρ1, v1, and t1. The flow over the larger cylinder has also a free stream density, v2, density, velocity, and temperature, which are given by relation as given here. So assuming that the viscosity and the sonic speed are proportional to temperatures, the power radical of temperature. Okay, so because that flow sonic speed is equal to radical of gamma RT. So RT and RT are gamma and gas constant are the same. So that we have left what? Radical of T only. So we can show this kind of the viscosity of 2 over viscosity of 1 gives us 2. So viscosity is related to temperature 2 over temperature 1. So we can get 2 here. Sonic velocity at second over sonic velocity at 1, the first gives us 2. Mach at 1 is velocity of 1 over sonic velocity of 1. So Mach 2 is equal to Mach 1. Obviously, it comes like that. V2 over A2, which is equal to 2 times V1 over 2 times A1, gives Machs are similar here now. So the flow is now similar flow. Again, when we substitute into the Reynolds equation, our Reynolds number of the second bigger circle is equal to Reynolds number of the second. So if the Reynolds number and the Mach number are the same, then the flow is similar, we call. Okay, so that is the similarity condition. Again, you can take some other example here, which is for the Boeing 747 Dreamliner, cruising at a velocity of 550 miles per hour at an altitude of 38 feet, where the free stream pressure is 432.6 pound per feet square, and the temperature 390 in the Rankine scale. So a 1/5 scale model. Now the model is 1/5 of the aircraft. The scale model of the 747 is tested. So አንድ አምስተኛ ነው። ይሄም ራሱ ትልቅ ሞዴል ነው። Anyways, so we are expected to calculate the required velocity and pressure of the test stream in the wind tunnel. ስለዚህ ምንድነው ዊንድ ታናል ቴስት ማድረግ መቻል አለባችሁ። ለዛ ነው ዊንድ ታናል ግቡና ኤክስፐሪመንት ስሩ ምናምን ብያችሁ ነበረ። አይ ዶንት ኖ እንግዲህ ገብታችሁ ይሁን አይሁን ምንም ኢንፎርሜሽን የለኝም። So for that, let's use so subscript 1 and 2 are denotes the free flight and the wind tunnel condition, okay, respectively. ስለዚህ CL1 is equal to CL2, CD1 is equal to CD2 are given conditions. So the wind tunnel flow must be dynamically similar to the free flight. ስለዚህ M1 is proportional to V1 over A1, which is proportional to V1 over temperature 1, because A1 is radical of gamma RT. M2 is also in the same way, like that. So V2 over radical of T2 gives V1 over radical T1. So this temperature and velocities are already given. So V2 is required. So V2 is equals to V1 times radical of T2 over T1. So 430 over 390. And velocity 550 is given. The 550 mile per hour ተሰጥቷል። 390 ራንኪን እና 430 ራንኪን ተሰጥቷል። እርስ በርስ ስለሚጠፋ we don't want to convert it to what you call that, the Kelvin scale. So we can directly use 430 is the T2 and 390 is the T1. So directly applying, we can get 577.5 mile per hour is the velocity. Again, we can compute the Reynolds number. So the Reynolds number is proportional to rho v L over mu. So from that, we can directly substitute instead of mu, we can use temperature. Okay, so applying temperature, we can compute this. So density of the second body or density of the first body, which is equal to V1 over V2 times C1 over C2 times radical of T2 over T1. So C is the chord, okay? So finally, we can find the density ratio of the two bodies. So V1 over V2 is equal to radical of T1 over T2. Just substitute in the place of this. So the density ratio gives 50. Once we get the density ratio from the perfect gas law or the gas law you have, pressure is equal to rho RT. So substitute just using this relation for point 1 and point 2, or for the body 1 and the body 2, what we can get, pressure 2 over pressure 1, which is equal to density 2 over density 1 times temperature 2 over temperature 1. So the ratio of density is 50 is given here. And temperature 2 is 430 and temperature 1 is 390 Rankine. So the ratio of pressure is 55.1. And that means pressure 2 is equals to 551.1 times pressure 1. And pressure 1 is already given. It is, I think, yeah. Pressure 1, somewhere it is given so that we can compute pressure. So that Mach 1, considering the flow similarity, that Mach 1 is equal to Mach 2. This happened. Okay? So you can convert it to atmosphere, or actually here it is pound per feet square, so you can change it. Once we understand this flow similarity, we have to differentiate the drag coefficient for different shapes or different configuration. For example, the flat plate, which is situated in the flow field, the density is too much high. The drag coefficient CD is 2. That means high value of drag. For circular or cylindrical diameter, or for circular body, the drag coefficient is still higher. It is 1.2. And when we come to the streamline shape, the aerofoil shape, you can find a drag of 0.12, which is smaller than others. Okay? And if you take a small cylinder, very small cylinder, it is 1/10 of the above cylinder. 1/10 of the diameter of the cylinder, very thin cylinder, but still it is having circular shape, so that still the drag is 1.2 because of the flow similarity. Okay, drag is high for the here. There is also another cylinder, and the cylinder is operating at higher Mach number, Reynolds number. Here, a Reynolds number is different, 10 to the power of 7. But for these two cylinders, the Reynolds number are 10 to the power of 5 and 10 to the power of 4. They are nearly same. But this one is higher Reynolds number. And the flow itself is turbulence flow, so that under that condition, there is 0.6. The drag is given like this. Anyways, the drag value is very small for slender or streamlined shape. That is 0.12 is the smallest drag, which you can observe from here. So this is all about the first chapter. So then we can continue with the second chapter. I think we have left 8 minutes to terminate this one. This session will be terminated after 8 minutes. Maybe we can continue after. So the second chapter is just about fundamentals and the principle of aerodynamics. So let's see what are those things. So with this chapter, we begin to build the basic equations of aerodynamics. And there is certain philosophies which we can use in this case that are the mass conservation principles, the momentum conservation principles, and the energy conservation principles. So we are going to see them. We are going to determine the suitable model of the fluid, of the fluid. So, and also we are going to apply the fundamental physical principles, which I already discussed, like the momentum, energy, and mass flows. Okay, so which are our so, in order to analyze the fluid flow, we have to use some amongst the three different models which are revolved on the aerodynamics. One is finite control volume approach, infinitesimal fluid element approach, and molecular approach are the three approaches on which we are analyzing the flow field. So the first one is finite control volume approach. So this is a finite volume. You can see control volume is there. And on that, there is a control surface. These are surface throughout it. So this is the flow field or the stream lines. So control, in this, the first picture indicates finite control volume fixed in space with the fluid moving through it. So the control volume is fixed in space, but the fluid is moving. These are the moving fluids, but the volume is fixed. Again, the second modeling technique on the finite control volume approaches, it is just finite control volume moving with the fluid such that the same fluid particles are always in the same control volume. So the control volume also moving, the fluid elements are also moving. So this is one of the approach. In the case of infinitesimal fluid element, we can take a very differential volume of element. This is differential volume of element. So the volume of element is dV. That is infinitesimally very small part of the volume. So infinitesimal fluid element fixed in space with the fluid moving through it. So look, this is the fluid moving through it, but the volume is fixed here. The volume is not moving. And when we come to the second part of this infinitesimal fluid volume element approach, here both the fluid and the volume also moving together. So in this movement, maybe there is rotations, there is also translations, and so on. So infinitesimal fluid element moving along the stream with the velocity v equal to the local flow velocity at each point. So at every point of flow path, we can find the local flow velocity. So dV is the infinitesimal volume, which is a moving volume here with the fluid. Okay. And in this case, the volume is fixed, but the fluid is passing or moving through the volume. So these approaches are some of the approaches which we use for the approximation or the analysis. The third one, sorry, it is, this is, the third one is the molecular approach. So in actual, the motion of fluid is a consequence of the means of motion of its atoms and the molecules. So the molecular model of the flow can be microscopic approach, wherein the fundamental laws of nature are applied directly to the atoms and molecules rather than to the finite volume or the infinite volume. Okay, so here the natural fundamental laws are applied to the atom level and the molecule level. That is a very sophisticated kind of analysis and very accurate. But this part of analysis is beyond the level of this course or beyond the level of our aerodynamic course because it is separately a huge part of analysis and the result also is realistic here. Okay, so now let's discuss about the specification of the flow field. So the flow field contains some variables. Okay, so some of the variables which included in the flow field are scalar fields and others are vector fields. So we have about 5 flow field variables. Pressure is a flow field variable, density, temperature, which are the flow field variables. But the velocity is the only vector flow vector, which is the variation of the vector flow field variable. So it is represented by u in the x direction, v in the y direction, and w in the z direction. So in 3-dimensional, we can represent it u in the I, v in the j, and w in the k. So this is a vector field. But pressure is just a point property. That is, pressure acting at a point is P of x, y, z, and t. So the 3-dimensional space and time also be incorporated. Time is the first dimension in this case. So x, y, z, and t are space and time fields. So, and this, the velocity vector is given by u by itself is u of x, y, z, t, v is v of x, y, z, t, and w is w of x, y, z, t. So these are fields. So these are actually, you can take a fluid element moving with a fluid. You see, this is the B approach of the infinitesimal small volume element. So at some point P1, you can observe velocity is tangent to that point, and x, y, and z are the coordinates, the Cartesian coordinates. So that P is P of x, y, z of the Cartesian coordinate plus the time. So time is also another important coordinate in our case. Density, temperature, all are x, y, z, and t. Again, velocity is velocity about x, velocity about y, and velocity about z are there. Okay, so now let's come to the fundamental laws of aerodynamics. That is conservation of mass, conservation of momentum, and conservation of energy. So let's see those things. What that conservation of momentum means. So the law of conservation of momentum states that the total mass of a closed system remains constant over time. And this principle ascertains that mass cannot be created or destroyed. It can only be redistributed or transformed